Hi everyone, this is Dr. Hopkins. I'm recording a few videos to describe some of the background and basic information for things that we use in our research. And what I'm going to start with are these three videos describing kind of the basics of lanthanides, something that you wouldn't cover in your undergraduate inorganic chemistry class. We'll talk a little bit about the basics, a little bit about their chemistry, a very little bit about their chemistry, about their structure, electronic structure, and spectroscopic properties. All right. So the lanthanides, where are they on the periodic table? Clearly, they're set off of the main periodic table down at the bottom. There's two sets of two rows, lanthanides, and then right below them are the actinides. They're sometimes referred to as rare earth elements, although it happens to be that they're actually much more abundant than many of the other metals that we use. And so the oxidation state, so lanthanide's the ground state electronic configuration. We go back to the periodic table and said, what's the ground state across that series? It's a xenon core, 6s2, 5d1, and then 4f. As you go across, you fill the 4f electrons. Okay, so those are those valence electrons. And then the most stable oxidation state that they exist in, and primarily the only oxidation state. There are a few that have some exceptions that can be +2, +4, but for the most part, all of the lanthanides will behave as +3 ions, and that is where they'll lose the 6s2 and the 5d1 electrons, and you're left with the xenon core and the 4f 1 through 14. Okay, so if we go across the series, now as you know, across any periodic table going from left to right, there is a contraction. The elements or the ions will get smaller. It just so happens that that contraction across the lanthanide series for the +3 ions is much more significant. Okay, so this will play a role in their chemistry, which we'll describe shortly. Okay, and then we look at, so one of the reasons for all of the strange behavior in terms of chemistry, spectroscopy, structure, and so forth has to do with the fact that the 4f electrons, so right now I'm showing the radial distribution, the 4f electrons actually lie inside the core electrons. So they're closer to the nucleus than the 5s and 5p core electrons. So your valence electrons are shielded by core electrons. And what that means is that they don't really participate much in bonding, okay, or in covalent bonding. And so this has some application towards their chemistry. So basically what you get is that once you've gotten rid of the 6s2 and the 5d1, you have a lanthanide 3+. They pretty much act like this large or small +3 ion or a hard acid, and they tend to form very ionic compounds, very ionic bonds. Okay, so you can just fit whatever kind of ionic ligands around them. They tend to like very hard bases. They're very oxophilic, so they like oxygens and so forth. The chemistry tends to be very similar for the lanthanide. So a neodymium chemistry and terbium chemistry is all very similar because they're the +3 ions. Just the fact that you've changed the number of 4f electrons doesn't really change the chemistry very much because the 4f electrons aren't participating in bonding. And so then what you'll get is a size dependence. So your large lanthanides will tend to have 9 coordinate because you can fit 9. So in this case, this is the aqueous system. You can fit 9 waters around the size of a neodymium ion pretty easily, whereas when you get to the smaller elements like erbium 3+, you might only get 8 around comfortably. So you end up with a size steric constraint that drives their chemistry. Of course, the chemistry can be a lot more complicated, and you can end up with ligands that drive structure and so forth, but I don't really want to talk about that. I just wanted to set up the fact that if we set up a system with the same ligands, the chemistry is pretty much the same. All we're doing is changing the number of f electrons. Say if we have a europium complex, a terbium complex, a samarium complex, they might all have the same symmetry. They all might have the same structure, but they will have different number of 4f electrons, which will affect their spectroscopy. Okay, so for the next video, we'll talk about electronic structure.